And if you have any technical mathematical question, then you talk to Vahid. Yeah. So this paper is co-authored by 3 wonderful people. One of them is Vahid, who is here. And then, so we are kind of the mathematicians. And then there's 2 people who are a little bit more machine learning people as our co-authors. This works now. Aha, okay. So we all know what a neural network is. Yeah, so I'm thinking of it, this is a family of functions. And this family of functions comes in the shape that the functions sort of compose by the layers, and they are parameterized by the weights of whatever this is. So this is a very abstract mumbo jumbo. And there's lots of geometry here, not just in using networks, but also understanding them. So for instance, if you have this parameterized family of functions, people wonder about what is the space of functions that this parameterizes. Sometimes people call this a neural manifold, although it's technically not a manifold. I call this here typically the function space. So I'm always going to use the symbol M for this neural manifold. And if you understand the space, then you have that people call this expressivity. Yeah? And there's the sort of whole approximation theory. What type of functions can you approximate with the network, which would be, you could take like an epsilon tube around your neural manifold and study this. Okay. And then once you have like a neural network fixed somehow, then typically we want to train it for some of the many purposes we saw today. And so typically this looks like this. Supervised learning, at least, you have some training data, and the goal is that you minimize a loss function. And what is important, it is a composed function of this shape. Here is sort of the parametrization map that you fixed when you fix your architecture of the network. And then you have a loss function that you can still choose, right? Does that make sense? So we're just all on the same page, what machine learning roughly means, okay? Good. And so I am a geometer, and I like to ask geometric questions. For instance, if I play around with the architecture of a network, then how does that change the geometry of this function space? And then what does this geometry have to do with this optimization problem? So how are these sort of things related with each other? And so in this talk specifically, I'm focusing on this question. Imagine I have my favorite sort of ReLU activation function or something, and I once have a network which is fully connected, dense, you have all the edges, and I once have a network where all the layers are convolutional. Then what happens to these questions? Okay. So what exactly is the impact of changing my layers from standard layers to convolutional layers? And so we're only going to study this in the sort of easiest setting that we can theoretically tackle, namely linear networks. So I assume that my activation function is not present, yeah, or it's the identity. So there's no ReLU here. Everything is just the identity because it's a theoretical paper, okay? So these dense sort of standard networks, they just multiply linear maps. Yeah, so this is just what this does. So it just multiply matrices. Here is an example where you have a linear map from R4 to R2, and then another linear map from R2 to R3. And then what you get, what is the function space? It's all linear maps from 4 space to 3 space, but the rank is bounded by 2 because of this bottleneck in the middle. Now, in general, this is always true for these linear dense networks. They just multiply a bunch of matrices. And so the space that you obtain is matrices of a bounded rank. And the rank is just sort of the smallest layer that you see. So this is the function space in this example. And it's nice because it's an algebraic right. And so we understand this for centuries and we know everything about it. Any questions so far? Very good. Now what happens if I do linear convolutional networks? I'm still sticking with linear networks where my activation is the identity, but now I have convolutional layers. For the purpose of this talk, I'm assuming that my convolutions are convolutions on vectors. So one-dimensional convolutions. But sort of most of the things I say you can also generalize to higher dimensions. We haven't technically written it down, but then you have to, yeah, I will show you. Okay. In any case, maybe first this one-dimensional convolution example. Now what happens to the graph of the network, it's not dense anymore. Yes, not all the edges are present, and you have weight sharing among the edges. So the orange edge has the same, they have the same weight, the green edges have the same weight, and so on. So now sort of the matrix that represents this first layer looks like this. Now the colors are a little bit not exactly the same, but this orange is this sort of yellow, you know, and this red is sort of this orange. It's sort of from the beamer, it looks better on the actual side. But okay, so this is now the matrices, they have now a certain shape. And I call these sort of matrices that look like that convolutional matrices. If you were to do the same thing with higher dimensional convolutions, you would get tensors here. You would get tensors, and the tensor itself would be of dimension 2 times whatever the dimension is. Okay, but in any case, I'm doing with the matrix case, and in general, these matrices, they are looking like this, where each row is a copy of the previous one, but it's shifted to the right by something. Yeah, so here in this matrix, they shift by 2. In general, it can be whatever. And people call this the strides of such a convolution, yeah, by how far you shift when you pass through the vectors. And the entries I'm not writing, they are 0. And the entries that are allowed to be something else than 0, they are always the same in each row, and they are called the filter. Okay, so I call this a convolutional matrix of some filter and some strides. And now, one of my first questions was, how does, like making a choice like this one, the choice of using these convolutions, how does this affect the geometry of the function space? Like what type of functions do I get now? Before I got this beautiful algebraic variety, and now I will not, I will just spoiler you this before I have this. Now we will get something which is not an algebraic variety anymore. It's going to be a semi-algebraic set. I will see right in a second.
Sorry, just to remind me, what was K for these special sets?
So K here, the small k is just the length of the filters.
Okay.
And so in this example, it's 3, and in this example, it's 2.
Okay.
So, I mean, I'm writing here for some reasons from 0 to k minus 1. It's my computer science. So science is in my 0. Okay. Another question. I know it's tired and we want to have drinks, but I'm very tired. I got up at 4, so I'm very tired. But okay. So I want to tell you not only that the function space is a semi-algebraic set, but I'm telling you what set it is. And so the thing, we know this is for a long time. If you multiply a bunch of these convolutional matrices, you get another convolutional matrix. So that's very nice. So these are closed on the multiplication. And you can easily compute the stride. If you know the stride of each of them, then the stride you obtain in the end, you just multiply them. Okay, very, very easy. Now, it's a little bit more delicate how to compute the filter. Right? So you know these W filters in each of the L factors, but now you multiply it. Then what do you get? That's the question. I am an algebraic geometer, so I like polynomials. That's my favorite objects of all times. And so I'm very happy to say that these can be multiplied by a polynomial multiplication. Or what I want to say concretely is that it's the same thing to multiply convolutional matrices as to multiply certain polynomials. It's the same thing. Okay. So this is a technical slide, but this is the message. Okay. So the technical slide, if you want to see how it goes, I have to tell you a map that identifies a filter or just any vector of length k with a polynomial. I'm now actually telling you a bunch of maps that could do that. So for any integer s, capital S, there is such a map that I'm writing down here. And what does it do? it just uses the vector as coefficients of a polynomial. But I'm not allowing all monomials, you know. So this is my notation for I only sort of allow monomials in x to the s. So this is a sparse polynomial. If you think of all monomials in small x, I'm not writing them all, you know, which is why sparse polynomial factorization is in the diagram. Does that make sense as a mapping thing? So given an integer and a vector, you can compute a polynomial. And now it's true that this multiplication of convolutional matrices means just to multiply these sparse polynomials in a certain way. Here it is. Here's the important equation. So this is just the product of these matrices here. Okay. I can use the pointer. I should use the pointer. Okay. So this is just the product of the convolutional matrices. It has a filter. I take this filter, I think of it as a polynomial. And that's the same thing as multiplying a bunch of polynomials, where each of them comes from such a map, and the capital S is sort of the product of the previous strides. And this is a funny exercise, it's just linear algebra. Okay, so when you're not tired after the drinks, you can do this lemma, prove to yourself, you know, that this is true. Okay. Oh, there's messages in the chat. Very good. It is S multiplied by. Well, it depends on what you mean by this. Well, I'm just defining essentially. Yeah, so the degree of the polynomials, you're correct. So the degree of these polynomials in the small variable x is f times k minus 1. But now I did a substitution, and I just said I make a new variable, let's call it y, and if y is equal to x to the s, then it would be just a polynomial. I don't know, just I didn't define this, but this is my notation for polynomials that look like this. That was, I think, the question. I hope that's okay. There's an answer. Okay, very good. Yes. So there was like this relation that we will use a few times. So I want to remind you of the strides, which are the small s's, and the capital s's, which I'm using here as my exponents of my variables in my polynomials. Namely, these capital s's are the product of a bunch of strides. And so in particular, if all strides are equal to 1, these capital s's are just all equal to 1, and I don't have to do anything fancy. And another extreme case, if all strides are larger 1, every single of these small s's is strictly larger 1, then all these capital s's are going to be distinct and becoming larger and larger and larger. And there is some realm in between, where some of the strides are 1 and some are not, you know, and then some of the capital s's are equal, but it's kind of an increasing chain, but maybe not strictly. But that's sort of the idea. Okay, now I can finally tell you. No, I cannot. Maybe I am still in Zoom or something. I have to press here. So now the map that comes from the neural network, I can reinterpret this not as multiplication of convolutional matrices, but as multiplication of polynomials. Yeah? So this is now my favorite way of writing the network parameterization map is now this one, which takes these sparse polynomials and just multiplies them. Okay. Very good. And now I can tell you, I mean, the function space of such a network is just all polynomials that can factorize. That's an interesting set to study that I'm not really aware of the people that have studied this type of polynomial factorization before. But that is what the set is. And so here is a theorem. So from this representation, if you know some basic algebraic geometry, it's pretty easy to deduce that the image of this map is a semi-algebraic set, which is closed in the Euclidean topology. So its boundaries, the Euclidean boundary is there. And we can compute its dimension. Okay, so the dimension depends on these small d's, which is kind of the length of these filters. And here's some pictures that Vahid made, yeah. So this is kind of cheated pictures, and not exactly cheated. I mean, this is an ambient space of dimension 5, right? Polynomials of degree at most 4 have 5 coefficients. And now this is a slice so that we can see something three-dimensional, right? So random slice. And this is how these guys look. Okay? Question? So this was like this sort of introduction.
Sorry, what's the blue dot?
Yes. So then we wonder, how do these guys look? Yeah. As this is going to be turning out sort of the unique singularity of these spaces. On the same time, it's also a boundary point. This point is interesting. It's both on the boundary and singular. And there is also here, you see the boundary. So now there's a relation between these two spaces. Okay. There's another thing we see immediately from this dimension formula. Namely, when is this dimension equal to the dimension of this ambient space? So here it is clearly not, yeah, because these are the curvy things. This happens if and only if all the strides are equal to 1. Because again, if all the strides are equal to 1, then all these capital S's are equal to 1. And then this number D is got this sum here. And then it's the same thing. And that's if and only.
What does that happen? The stride is 1.
Again?
If all the strides are 1, what does the network look like?
I mean, that is sort of the most, if you were to use a convolutional network, it's sort of the first idea that you might use. I mean, that you shift always the convolution one step down. So there is kind of a difference, which we don't really understand from an applied point of view why it is, but there is a geometric difference between if you shift down once or further. Sort of.
Still have a filter about it.
Yeah, there's a filter, but just the question how far the filter changes.
Sorry.
Over the vector. Yes, I mean it's late, I know, and there's lots of symbols here, but I didn't really know how to shorten it even further. But let me give you a summary slide. So what we know so far, there is linear dense networks, which is just rank-bounded matrices, and that's an algebraic variety. Now, for these convolutional networks, the function space is not a variety anymore. It's rather a semi-algebraic set. For those who don't know what it is, algebraic variety means cut out by polynomials, and this means polynomial equations, and this means cut out by polynomial equalities and inequalities. So here I have a whole curve, and in this world I'm allowing a segment on the curve. Okay, that's sort of the difference, but they are very different. And this, you'd think if you do optimization, that this is very different. If you do optimization over variety or over something algebraic thing, which we would do in machine learning. And we have this sort of special case that all strides are equal to 1, then this is not 2 vials, because then we have some beautiful vector space and like a full dimensional thing that sits there like an oval or something, you know. But here this can become pretty crazy the moment that you allow these larger strides. So a first hint, here's a very cute sketch. Okay, so imagine we're in the plane. This would be a full-dimensional semi-algebraic set of the plane. I tried to make kind of the unit ball of the 4 norm, you know, that would be an actual example of it. And what you would think is that when you do optimization, that you're often going to land on the boundary, right? So the boundary of these things is typically not empty. And it is true that when we do machine learning, we train a network, we run it. We did these experiments in the previous paper, that we often land on the boundary. So here is again my summary so that you know my notation. Training a network means minimizing this loss. And I want to stress again, the loss we do actually train in parameter space, not in the function space. So in some sense, this picture is misleading because I'm only drawing for you sort of what happens in the function space optimization problem, but machine learning and the gradient descent, everything actually happens here. So I cannot really say that the critical points are on the boundary, rather than the critical points when you map them. You know, so I have this, you know, the critical points, you map them forwards, they're often on the boundary. Okay. Now, what do I want to say next? I added this entry here. For an algebraic variety, there is no Euclidean boundary. So this question, if I often land, that doesn't even make sense. Yeah, so that's not so interesting. But there's other points that are interesting on algebraic varieties, and we heard some talks about them today, singular points. So have an algebraic variety like this one, then there are special points that exist and are relevant, and it is in fact true that we often have those when we do machine learning. So this was again the matrices of bounded rank. Now, some of you, I guess, know the Netflix problem, yeah? No, do you know the Netflix? Does someone not know the Netflix problem? Somehow, essentially, you're asking for user profiles, and can you find? You can store each user profile if you have a feature vector as a row vector in the matrix, and then you make a conjecture that there's just 7 different people on the world, it's types of people on the world, okay, what they like to watch, etc. So you think that if you would put all people of the world into this huge matrix, that maybe it has rank 7 approximately, okay? And so you can then use that to predict what people like to watch, right? And so when you do these sort of low rank optimization problems, you're looking for a rank 7 matrix, but it kind of with positive probability outputs you like a rank 5 matrix. Yeah? This sort of behavior happens, which is desirable, for instance, in a Netflix problem application. So what I'm saying is that for algebraic varieties, the singular logos is very often non-empty, and then we might land there when we do optimization, and that can be a feature or a bug depending on what you're looking for. Whereas in this situation here, this geometric picture of my 4-norm ball in the plane, there is no singular points. And that's here in general. Yes. There's only the boundary, and the boundary is relevant for the optimization, but then there is no singular locus. So, and now what I want to get at is that these sort of guys, these convolutional networks, where I have strides that are larger than 1, they are like the first instance of a network where you have both singular points and boundary points. And we were interested, for instance, in our paper to see how often I somehow get there. Because this is what we did in previous studies with these sort of models. Okay. Now I will summarize. For me, it was a very surprising theory because I was trying to compute sort of we never found them in the experiments. When we did experiments, we sort of didn't really get these singular points or boundary points. And then, Vahid and I, we could actually prove that this is wrong. So what we rather proved is that almost never we are going to land on a singular locus or the boundary. So with probability 0 is going to happen. Okay, so now, yeah.
Could you just say exactly that again?
Yes, I will also give you a precise theory. But so here we know that we with positive probability land on a singular locus, here with positive probability we land on the boundary, and here with probability 0, we would be singular or on the boundary. So with probability 100, we will be smooth interior points.
So when you say probability over
I will give you a very precise theory. I was just sort of wanted to make it not so technical. It's 4 p.m. I don't know. Okay. Now let me get to the theorem. So the theorem, to give a precise, what we only proved it for using if you use the square laws. So for those who don't know, so it's a squared error, we optimize it. So say you have some training data, input vector, output vector, pairs, standard setting, and supervised learning. Now you can just compute the squared error. I mean, that's your matrix T is like the linear map that we're supposed to use, and we can just see, we want to minimize this function. This is a very algebraic specific thing that we can prove things. But of course, I want to stress one more time that when we want to set this up in theory, we are actually not minimizing this, but we are minimizing its pullback into the parameter space. So it is sort of not enough to understand how the singular points and the boundary points look like, but you also have to understand this composition and what are the critical points of the parametrization there. Okay, here's now finally the results. So if you train convolutional network, this theorem here, the easy version, is when every single stride is larger 1. We have a 1 which is more general, but for the purpose of this talk, if every single stride is larger 1, and capital N is just my amount of data, how many input output pairs, just large enough. Okay, we can see how large one. Then, for almost all such n tuples of data, we have, and this is now an every single critical point satisfies that it's either just a zero function or it's a smooth interior point of the function space. Let's pass this theorem and we can see there are some questions. So here was for almost all, you could take any probability distribution on this set. Yeah. So what we prove technically is, there is an algebraic hypersurface in this space, the discriminants, yeah, like in the previous talk. And if you're outside of that discriminant, then every single critical point is smooth interior points or zero.
And but is this not true for dense networks?
For what networks?
Dense, fully connected networks?
No, exactly. It's not true. I mean, we can go back to the table again. I will actually do this on the next slide, I think. I mean, we prove here in particular that we almost never land on a singular glucose unless the 0 point. But here, this is not true. No, it's not true for dense networks. It's not true in any of these settings. So, and that was sort of the first time. Yeah, that's why we wanted to write the paper, because we sort of knew how there's lots of work on these dense networks. There's a little bit less work on the sort of these type of networks. Yeah.
If you have one case where all the skies are equal to 1, where all the skies are greater than 1, can you consider the case?
Yes, we have a more technical theory. I can give you a little bit a hint of how it looks in the last, and you can read the paper, right? The paper exists, but yes, we have something for in between. Essentially, if we have an architecture where some strides are 1 and some are larger 1, then critical points can either come from the stride 1 parts or from the stride larger parts. And the ones from the stride larger parts also still satisfy this. But then the ones that come from the stride 1 parts there. Yeah. I will get to that in a minute. I want to add one more row to my table because I left like a blank space here. And what is other questions that people in like the theory of neural networks study is not just sort of where do the critical points lie, like are they singular or something, but what is their quality? So people care a lot about the global minima, the local minima, the saddle points, And so in this sort of analysis of the quality of these critical points, it's important to distinguish between the true or pure critical points and the spurious ones. Where the spurious ones are those, again, we're doing this in parameter space, are those critical points in parameter space that when you map them, they're actually not critical points of the actual loss. And this can happen, of course, because I mean, we kind of want to solve this problem, but we can't do it in practice. And so for machine learning, we're using this over-parameterized spaces, and now we can create descent there, but we might introduce new critical points. Okay? And these spurious points, also with positive probability, when you pick training data, you do the squared error loss, you're going to get critical points. And so there is these papers that try to prove that linear dense networks always converge to like the global minimum or something like that. And it's very important in those papers to understand, to like sort of get rid of, like take care of these sort of spurious points. And people prove that they're always saddles and it's nice, in and out and stuff like that. Okay, so they often appear here, they often appear here, and also our results, in fact, is a little bit stronger than the previous theory. we showed that with probability 100, you will not get spurious points. So if you were to do a convergence analysis, you wouldn't have to take care of them, for instance. So here is that version of the theorem. Here I added this yellow part. So for almost every data choice, all the critical points are in fact the regular points of the parameterization map, and that's just basic differential geometry. So they cannot be introduced by the parameterization map. So they have to be honest. They're as nice as they can be. Yeah? They're honest, true points of the problem that we care about, and not even any degenerate points or something like that. Okay, so now I can talk a little bit about this mixing of stripe 1 and not stripe 1, and a little bit how the singular points look, and so on and so on. But you could have questions now already. Sing again. Oh, right. Yes, see, I use change notation here a little bit. Yes, so actually, now let's see. I mean, when I write my filters as vectors, then I said they have k entries. That's the k. But then I think of them as polynomials of degree d. And then, you know, so if I have a polynomial of degree d, it has d plus 1 coefficients. So like these d's are like plus minus 1 equal to k. If I think of them as matrices, you know, so they are related. Yeah, yes. So this is just if there's these different words. You can think of these convolutions as polynomial multiplication or matrix multiplication. And then in the matrix world, it's easiest, or this is how squared error loss is implemented to deal with the matrix. It's not typically implemented in the polynomial words. So I didn't want to confuse machine learning. Okay, yes, very good.
When you teach the Singularities was the weekly umbrella, right?
Yes.
And so it was the method simple. The entire dimension.
Yes, the homogeneous not. Which is why we always see this zero, yeah, just the vertex of the code. Yeah, it's called. Very good observation. And I can see the video better. Okay, other question? Okay, then I spent like 10-15 minutes. Okay, so I want to go actually back to this picture. And you also sort of see from this picture that this function space should be sort of related to that function space. So let us understand what the argument is. So here I have degree 4 polynomials in both cases. Okay? And here I'm factorizing them into 2 factors of degree 2, but one factor is supposed to be special because the monomial x is not allowed to appear. This is what this notation meant, right? So here I really have like a plus bx plus cx squared, but here I only have like d plus ex squared, like there's no exponent. And here I can almost do the same thing, except that the arbitrary quadratic factor is now supposed to split into 2 linear terms also. And that's why this function space is strictly larger than this one and contains it, because it's just a further step to factorize even a little bit more. And so here is this diagram, you know, you first sort of merge the straight 1 part together, and then you would get a map here where all strides are larger 1, and that's our general idea. And this is how you can then prove theorems about the mixed situation. You first multiply the stride 1 parts together and survive. So I'm not giving a technical definition here, but I'm just saying if you look in the polynomial world, you merge all those layers where these exponents here are equal, these capital S's are equal, and you keep doing it until it stops, and then you end up with a neural network where you have this strict increasing of these capital S's, which was equivalent to the strides being larger 1. And so that way I can start from a neural network and I make a new one and I call this the reduced one. Okay, I just something that we do. Okay.
For these new points, the points which are both boundaries, for instance, singularities,
Unique in what sense?
as in, is there only one such point that they can?
Oh yeah, I will tell you a theorem. I will tell you exactly, we know all the singularities. And in fact, it's very beautiful because the singular points are just smaller function spaces. And this was known, I mean, it's true for the linear dense case. If you know determinant varieties, you have all the matrices of bounded rank. What's the singular locus? All matrices of one rank less, which is again coming from a neural network. So you have a stratification like this, and we also have a stratification that the singular points come exactly from smaller neural networks. There's this rising young machine learning theory star, Nadav Cohen, and he conjectured that this is always true for any network, even if you do ReLU and so on, that you say something like that.
So didn't you say that for any singular network? That's true?
Yeah, it's true, because it's true for dense networks, yeah. I'll show you the theorem in the convolutional case. In the dense networks, we can do it as an exercise in the drink session. So first of all, we do this sort of reduced procedure, right? So I'm just merging some of the layers together. It's always happening, what happens in this picture, that you might make your space larger, right? We see that the space in general becomes larger. So this tilde is my reduction thingy. But the Zariski closure is still the same. So now I know that not everybody here is an algebraic geometer. Zariski closure is just the closure in the Zariski topology, meaning you take the smallest space, which is cut out by polynomials where you live. So in this example, which I had, where you take the unit ball of like a 4 norm in the plane, the Zariski closure will be the whole plane because there is no polynomial that only vanishes on this interior of this ball. But in general, these are semialgebraic braids, and they are the same if you do this reduction procedure. Hence, if I care about singular loci, singular points on the interior of these spaces, it's enough to do it for these reduced guys. Okay, and here's now our theorem. So if I have a reduced sort of neural network, but if it's layer 1, it's boring. I mean, a layer 1 doesn't do anything. It's the identity map. Yeah? So it's just all polynomials. If it has more than one layer, then it is never smooth. It's never smooth. It's a cone of some degree that's positive. And so the 0 is always a singular point. And the other points are just, it looks a lot, but it's just a union of all function spaces of neural networks that are strictly contained. This is what I'm writing here. I'm going over all these integer vectors such that I have function spaces strictly contained in the one I'm looking at. And this is all the singular points. And this is sort of my geometric intuition of the sets. But maybe you want, is this computable? It is, but then it's not, I cannot understand it anymore. But if you do this, you could implement. Yeah, this is just some combinatorial game. So it's implementable and it's also understandable. That's the question, right? So it is not always like a unique singular locus. There are several components, and how many you can compute in principle from this thing. Very good. Okay, then I think the last thing I want to just give a hint about is that so we also studied these boundary points, but well, as an example, we would just skipping it. I mean, here the singular locus just has a single component. Again, we would be like in a 5-dimensional space, and we took a slice. Once I took a slice, it's only a point that survives. But in the truth, no, it's a 3-dimensional thing. It's a 3-dimensional thing and a 5-dimensional thing. Okay. So the boundary of these spaces, right? You see that since that guy is contained in him, he has more boundary points that sort of cut this one out from the bigger one. And this just comes from the fact that I was merging a bunch of these stride 1 layers together. And so in the boundary discussion that we're doing, we're distinguishing of also two types of boundary points. But again, if you do the reduction, the actual function space gets larger, but there's a risky closures are the same. So you can make this sort of containment chain. And now you could have either boundary points that also exist on the reduced version, or boundary points that come from the fact that the smaller guy sits in the larger guy. There's two types of geometrically different boundary points. So we call them, like technical definitions, but yellow guys and orange guys. And this does not fit with the colors of this picture, but I mean, the dashed line is the one that comes from the stride one. This would be the orange boundary points. And the yellow boundary points is in this example the blue point, which also happens to be a singularity. And we cannot give a full algebraic characterization of the boundary, only of the stride one part. But what we can prove is that the ones that come from the reduced one are always lower dimensional than you think. And this is a funny thing. I don't know how many of you have thought about very low dimensional semi-algebraic sets in high dimensional spaces. Crazy things can happen. I mean, you think that the boundary always has one dimension less, but that's not true anymore. Like in the Whitney umbrella is one of these examples where the boundary can all of a sudden be very tiny. And we actually prove, as you see in this example, this blue point has 4-dimension 2, not 1, with respect to the whole space. Which also gives some sort of further reason why in this theorem that I showed you, we're not going to hit those points, because they're even tinier than they should be. I don't know what to say. Okay, and I think so this is then a conclude, so that you can look at the slide again, right? So here we have boundary point and hit them because they have some 4-dimension 1. Here we're not going to do that. And then I am done, yes. So we can go earlier to the drinks.